In this lecture, we are going to discuss about the Lagrangian dynamics, the degree of freedom, the constraints, formalism of Lagrangian dynamics, and principle of least action, D'Alembert's principle, as well as Lagrangian equation of motion. Lagrangian dynamics. So before going to Lagrangian dynamics, let us understand some history of the Lagrangian dynamics. It's a mathematical framework to describe motion of any physical system. Now it was developed by Joseph Louis Lagrange and during the year 1700s. The motion of the physical system is described by a quantity called Lagrangian. So it's represented by the letter L, and the Lagrangian L is a function of the coordinates as well as the velocity. For example, x is the coordinates, x dot will be the velocity. Similarly, y and y dot, depending on number of coordinates or degree of freedom it has. Now, usually the Lagrangian is defined as the difference between the kinetic energy and the potential energy. So L, we can write it as the kinetic energy K minus the potential energy V, right? Or sometimes the kinetic energy is represented as T, so you can also write L is equal to T minus V, where T is the kinetic energy and V is the potential energy. Now, using the Lagrangian L, one can derive set of equations known as Euler-Lagrange equations, or simply you can write Lagrangian equations of motion. Lagrangian equation of motion, which describes how the system's coordinates and velocities change over the course of the time. Now, these equations are based on the principle of least action. Now, what does this principle of least action says is that the path taken by the system between 2 points in space and time is one that minimizes the action. That means it undergoes least action, and it is related to Lagrangian. Now, understanding this principle of least action, we can consider so here we have point I, that is the initial point, and here we have F, the final point. Now assume there are different ways. So this is one way to reach F. This is the initial point and this is the final point. And if you have another point, something like this, okay, so this is IAF and this IBF. Now for example, if there is a particle, and this particle would take the path which has least actions. Okay, so either of the path which has the least. For example, if A is having the least actions, then the particle would take this particular path to reach F, then B. So this is called the principle of least action. This is also based on Fermat principle. Okay. Now, a few advantages of using Lagrangian is that it is concise and elegant for describing the system's behavior. It is also applicable to wide range of systems in classical, quantum and relativity. Then it also allows the use of symmetries and variational principle for analysis of complex system, and the system can include from simple harmonic oscillator to motion of planets in our solar system. So these are the different systems where we can apply Lagrange. In Lagrangian dynamics, we will be discussing about the degree of freedom. Right. Now, what is degree of freedom? Now, in any generalized coordinate system, any motion to describe any motion can be described by a set of variables which are independent. Now, for example, in Cartesian coordinate system, we have like x or y and z. To describe some motion, we are using the help of these x, y and z. Now this x, y and z are independent of each other. They do not depend on any of the other coordinates. For example, z is not a function of x comma y, right? So this is called independent variable. So such motion or such coordinates are called, or the number of independent coordinates that are required to describe the motion of a body is called the degree of freedom. So here we need to understand what is generalized coordinates. Generalized coordinates are coordinates required to describe the motion. And what about the degree of freedom? Degree of freedom is number of generalized coordinates. And this must be independent. Okay. Here for generalized coordinates are also they are also independent coordinates. They do not have any functional relationship with each other. For example, x will not be a function of x of y comma z. Now let us check how to identify the number of generalized coordinates and the generalized coordinates in general. So how to identify generalized coordinates? From Lagrangian. If the Lagrangian of the motion of the particle is given, then how will you identify the generalized coordinates? For example, the first one, Lagrangian L is equal to half m L square theta dot squared plus mgl cos theta. Now generalized coordinates, we will write GC for generalized coordinates, that is generalized coordinate is theta, because here we have as a function of theta, and here we have theta dot, its first derivative with respect to time. So generalized coordinate is theta. How many generalized coordinates are there? Only one, so degree of freedom is equal to 1. Now let's take the second example, that is Lagrangian is equal to half m r dot square plus r square theta dot square. So plus mgr cos theta. Now we have theta and its first derivative here, r and its first derivative. So this will be generalized coordinates equal to theta comma r, or r theta, and degree of freedom f is equal to 2. Similarly, looking into the third option, Lagrangian is equal to half m r dot square plus r square theta dot square plus r square sine square theta phi dot squared plus so this much only. Now generalized coordinates equal to, here we have r dot, theta dot and phi dot. So r, theta and phi, these are the generalized coordinates, and degree of freedom is equal to 3. And if at all there is time will never be included in the degree of freedom. So time frame or time coordinates, time is never included in degree of freedom. Please make a note of this. This is, time is never in degree of freedom. Understanding the constraints. What are constraints? So what are constraints? These are physical conditions. So constraints are physical conditions that conditions of restrictions. Okay, so this is physical condition of restrictions that are imposed on. So imposed on motion of a body. Which cannot be taken back or which cannot be broken during its motion. Now for example, if there is a table and this is the top of the table and the ball is moving here in all different directions, so this is 2 dimension and it has 2 degrees of freedom, so degree of freedom is equal to 2. Now I restrict it in 1 dimension, so I I restrict its motion along its this particular, for example, I am tying it to something. Okay, so it can move, cannot move in all direction, but it can trace a path, something like this. So this is called a restriction. Okay, so each restriction you add, the number of degrees of freedom get reduced. So degree of freedom can be equal to 0 provided all the directions of motion are being restricted. Okay, so degree of freedom equal to 2 here. So these are called constraints. So what does constraints do? Constraints reduces the degree of freedom. So for each particle, the constraints reduces the degrees of freedom. The more constraints you have, the lesser freedom you have. The more constraints the body has, the lesser the freedom has, lesser the freedom body enjoys. Okay, this sounds philosophical, but it's good. How to calculate the degree of freedom when dimension, the number of particles and the constraints are given. So we have to find out the degree of freedom we have when dimension of the system is given, that means dimension of where the system is, that is called the dimension. For example, if it is in 2 dimension, particle can be moving in 2 dimension, 3 dimension or 1 dimension, and number of particles, that means it can be n number of particles in 1 dimension, n number of particles in 2 dimension or whatever. So dimension is given by d, number of particles n, and the constraints. Now what are constraints? Constraints are restrictions. How many restrictions are there? Okay. So that's equal to c. So in that case, the degree of freedom f is equal to d times n, that means the dimension times the number of particles minus c, which is the constraints. Let's look into some examples. One, particle moving in 3 dimension randomly. So this is the 3 dimension, and one particle is moving like this. Okay, this is the particle, and its motion is given as this one. Okay, now here the number of particle n is equal to 1, d is equal to 3. Constraints, number of constraints, there is no constraint to it. It can move in any direction, so constraints are 0. So the degree of freedom f is equal to 3. Let's look into another example. If this 3 dimension and there are 2 particles, so here is one particle and another particle over here, and they can move in any direction, but they are connected by a rod. So the number of particle is equal to 2, dimension is 3, constraint is 1. There is one constraint, and thus the degree of freedom f will be equal to 2 times 3 minus 1, that's 5. There are 5 degrees of freedom. Now suppose if there is no constraint here, this will be moving in all possible directions, and this also will be moving in all directions. So there will be 6 dimensions or 6 degree of freedom. Now to understand another concept, that is let's look into another question. All particles, there are 3 particles. Here we have a triangle, and on the vertex of all triangle we have 3 particles, and all these 3 particles are connected by this by rod, inextensible rod. So there are 3 particles, so n is 3, and dimension is let's take the dimension to be 3. So dimension is 3, and constraints is also equal to 3. So the degree of freedom f is equal to nd minus c, which is equal to 6. Now just to understand a little more about this interconnection, if all the particles of the system are interconnected by rigid rods, then what would happen? Now let's take one more example, that is the 4 particles at the corners of the square or the rectangle. 1, 2, 3, 4, and all are interconnected, and now there is another connection between diagonally connected. Now the number of particle is 4, the dimension is 3, and constraints, so 1, 2, 3, 4, 5 and 6. So these are 6 constraints, so 6. So number of degrees of freedom, or f is equal to 4 into 3 minus 6, which gives you 6. So we will conclude by saying that if all the particles are connected by a rigid rod in 3 dimension, if all particles are connected by rigid rod in 3 dimension, then degree of freedom f is equal to 6. as an extension to what we have learned in now, that is the all particles are connected, all particles are interconnected by rigid rod. This simply means that the object that we are talking about, or the system of particles that we are talking about, system of particle is a rigid system, and this system is called rigid body. That means as a dimension of the rigid body, you consider system is rigid, or a body is rigid, if the distance between two points are same, it does not change. If the distance between two particles in the system does not change, if this does not change, then this is called a rigid body. So for 3 dimension, or you can say in d dimension, so any dimension, so in any dimension d, the degree of freedom is given by d into d plus 1 by 2, and this is for only rigid bodies. For rigid body, the degree of freedom is given by d into d plus 1 by 2. So for 3 dimension, f is equal to d is 3 into 4 d plus 1 by 2, that's equal to 6. For 2 dimension, f will be equal to 2 into 3 by 2, so that's 3. And in 1 dimension, for rigid body, f will be equal to 1. Something to note here, that as the number 1, time is never included as degree of freedom. Time is never included or counted in degree of freedom. And the second one, particle moving in a surface, so degree of freedom is 2. Any surface, for any surface, if particle is moving only along the surface, its degree of freedom is 2. And that's the last note. Particle moving on a line, its degree of freedom f will be equal to 1. Now particle moving in a surface, I would like to draw this as the surface. So this is the surface, and this is the particle moving in this surface in this way. Okay, so this is actually the degree of freedom f is equal to 2. Okay, now if I have 3-dimensional this one here, and this is the constraint that it has, and the particle starts from here and it moves along this line. If it moves along this particular line, even though this line is in 3 dimension, the degree of freedom f will be equal to 1. Coming to the type of constraints, or types of constraints. First is related to geometric constraints. Now the first one is Celeronomic constraint. SCE, Celeronomic constraints. Second one is Celeronomic and rheonomic. Rheonomic. And second is holonomic and non-holonomic. And here we have the last one, the conservative and non-conservative. Now the Celeronomic constraint is time independent. So Celeronomic stands for time independent. It does not depend on time. Okay, and about rheonomic, this is time dependent. Constraints. Okay. Holonomic means equality. If you put an equality sign, for example, x square plus y square plus z square equal to r squared. So this is an example of holonomic constraint. And about non-holonomic, so non-holonomic means we write x square plus y square plus z square less than or equal to r square. So this is an example of non-holonomic constraint. And holonomic constraints are integrable constraints, and while this is non-integrable. Depending on how the constraints affect the energy of the system, the constraints can be either classified as conservative or non-conservative constraints. Now constraints, the conservative constraints are the constraints that do not cause any energy loss. There will be no energy loss, and which means the total energy of the system would remain constant, and though the energy can be converted from one form to another. For example, the kinetic energy can be converted to potential energy or sound energy. Okay, so different forms it can change. Now examples, the constraints due to gravitational potential energy, elastic potential energy, or the conservation of angular momentum. Okay, so these are examples of constraints where we do not which do not undergo any energy loss. Coming to the non-conservative constraints, conservative constraints leads to loss of energy. Total energy of the system decreases over the time. Good examples are friction, air resistance, and viscous drag force. Now, why do we need to understand these constraints? Is because understanding the constraints of a system will be helpful in understanding or predicting the system's behavior or motion over time. D'Alembert's principle. Now, according to D'Alembert's principle, a system in static equilibrium has the net force, so sum over the force Fi is equal to 0. Now we can also write this in the form of the force. Now sum over the force applied on ith particle times delta Ri. Now the delta Ri is the virtual displacement, so this one plus sum over the Fi, this is the force due to constraints, times delta Ri equal to sum over Pi, that is the change in momentum, Pi dot times delta Ri. Now this is the D'Alembert's principle. Now the first term represents the work done by actual force, or applied force. Now this is the work done by constrained force. And this work done by constrained force is equal to 0, and this is called the principle of virtual work. So principle of virtual work says that the work done by the constrained force is 0. Now this is the work done by opposing force. So this is from D'Alembert's principle, and we can also write that from this the same equation we will name it as 1, and this 1 can be written as sum over Fi applied dot delta R I, this is force, is equal to sum over, and this Pi we will write it as m I v, that is the velocity, dot, that becomes the acceleration, vi dot delta Ri, and this is also a vector, this is another vector. So this is similar to the Newton's third law, and this is called D'Alembert's principle. it's from D'Alembert's principle. So this is from principle. We are deriving the quantity called generalized force. Generalized force. We had generalized coordinates, generalized momentum or velocity, and now we are defining a term called generalized force, which is represented by Qj, that's equal to total time derivative, that is d by dt of dou by dou Qj, that is the Q represent the coordinates with respect to t. I mean dou by dou Qj of t minus dou by dou Qj of, sorry, this is Qj dot times t. So now this is in terms of t. What is t? T is kinetic energy, and similarly in terms of the potential energy we will get Qj is equal to total time derivative of dou by dou v d by dt of dou by dou Qj dot of v minus dou by dou Qj of t. Sorry, this is v. So this is the generalized force in terms of kinetic energy, and here v is potential energy. Qj represent the generalized coordinates. Now from here we can write the Lagrangian equation of motion, which is nothing but the total time derivative of dou L by dou Qi dot minus dou L by dou Qi is equal to 0, and where L is equal to t minus v. Now if you consider this as equation 1 and equation 2 here, 1 minus 2 would give you this, so this is t minus v, so 1 minus 2 should give you the Lagrangian equation of motion. So once again rewriting the Lagrangian equation of motion. Equation of motion, that is total time derivative of partial derivative with respect to dou Qi dot of L minus dou L by dou Qi equal to 0. Now in any case this Lagrangian equation of motion does not fall to be is not falling to be equal to 0. That means when we take the total time derivative of dou L by dou Qi dot minus dou L by dou Qi is not equal to 0, and you are getting some value, that is, let it be Qj, and this is called this is due to the this is nothing but force force due to non-conservative constraints. So force just arised due to non-conservative constraints, and this Qj is called generalized force. To understand the generalized force, let's take a few numerical problems. So generalized force. So Qj is equal to, in terms of kinetic energy, d by dt of dou t by dou qi minus dou t by dou qi. Now here you have dou qi dot. Now for the first case, we will take the kinetic energy as half m x dot square. So this is like half mv square, where v is equal to x dot. Now that is along x direction. Now applying to this formula, total time derivative of dou t by dou qi dot, which means dou x dot minus dou t by dou x. Now the second term, dou t by dou x, t is independent of x, it is x dot, so we can write d by dt of dou by dou x dot of half m x dot squared. So this gives us d by dt of the dou by dou x dot of half mx dot square is nothing but mx dot. This gives us m as constant, x dot with respect to d by, that means d by dt of x dot is nothing but x double dot. So the force Qj or Qi is equal to mx dot. Now this Qj is nothing but force along x direction, so you can write Fx is equal to mx double dot. Now just case for the second question, let's let it as t is equal to half m r dot square plus r square theta dot square. So here we have the generalized coordinates. So generalized coordinates is equal to r dot and r and theta, and generalized force. So generalized force should be in terms of fr and f theta. So to find out fr, that's equal to d by dt of the partial derivative of dou by dou r dot of t minus dou by dou r of t. Now this is equal to total time derivative of dou t by dou r dot. So r dot is 2r dot and m. So m r dot, mr dot minus dou by dou r of t. So it's 2r and m. So this gives us 2 gets cancelled. So theta dot square, so m r theta dot square, so m r theta dot square, so this becomes m r double dot minus m r theta dot squared. So this is Fr, that means the force, generalized force in the r direction. Similarly, and write T as equal to half, this is the kinetic energy, half m r dot square, the question, that is r square theta dot square. Now we have done Fr, that is the generalized force along r, that is mr double dot minus mr theta dot squared. Now f theta is equal to d by dt of dou by dou theta dot of t minus dou by dou theta of t. That's equal to d by dt of dou by dou theta dot of t, which means 2 so m r square theta dot m r square theta dot minus dou by dou theta, so this, the second term is 0. So this we have to differentiate with respect to t on m r square theta dot. So since r square and theta dot are variables here, we have to differentiate using UV differentiation. So m taking r square, so it becomes 2m r into r dot theta dot plus, now with respect to theta dot, m r square theta double dot. So this becomes the f theta, that means the generalized force on theta direction. Now as a work out problem, we can find the generalized force for the kinetic energy T is equal to half m r dot square plus r square phi dot squared plus z dot square. So this is r, phi and z. This is in cylindrical polar coordinates. So you will have f r, f phi and f z. These are the generalized force. You can please find the answer to this. Now coming to the generalized force in terms of potential, so we can write Qj equal to total time derivative of dou V, the potential, dou Qi dot minus dou by dou Q of V. So this is the formula. And suppose we have a potential which is a function of q and q dot given by 1 plus q dot squared. So this is the potential given. We are asked to find out the fq. So qj equal to total time derivative of dou v by dou q dot minus dou v by dou q. Now this is equal to d by dt of dou v by dou q dot is v by dou q dot 2q dot. So 2q dot minus dou v by dou q is 0. So time derivative of 2dq dot is nothing but 2q double dot. So this is fq. Now as a workout problem, so practice questions. We can find out the generalized force V is equal to 1 plus q dot by q. The second question, V is equal to 1 plus q dot by q squared, and third one, V is equal to q dot by q. Answers to the questions. First one you should get as 1 by q square. Second, for the second question, answer is 2 by q cube, and for third it's 0. So try to get this answer and please let me know.